Hi, my good people. So I'm going to quickly go over electrical circuits and just the basics for it. So we're going to go through the parts that are not the calculations, more of the vocabulary parts. So the first thing you need to know is that an electrical circuit is a one-way path in which electrons flow from the voltage or current source out to the device and then back to the battery. So it's a one-way path that's illustrated by the electrons and the arrows. Voltage goes in one direction. There are three components of an electrical circuit, but sometimes you can have a simple electric circuit with just a battery and a lamp, as in the schematic on the right-hand side. The battery allows the current to flow from the battery to the lamp, through the lamp, and then back to the battery, thus making a complete loop. However, you would need a switch to turn it on and off, otherwise it would just stay on. Electric circuit is the movement of the electrons in a simple circuit consisting of a battery, a switch, and a light bulb. Now you're going to see the movement of electrons in the animation that I'm going to show you, but the current actually flows opposite. Conventional current is said to flow the opposite way. So when I bring this up, you're going to see we have a battery, we have a wire, and these little blue lights represent the electrons. The switch is going to turn on and off so you can see how this works. So switch on. The electrons are coming out of the battery, going through the lamp to the switch, back into the battery. So that is the flow of electrons. The flow of conventional current is the opposite way. So just keep that in mind as we go through this unit. The electric current is the flow of the charge. Conventionally, this is the flow of positive charge. However, in a simple circuit, such as that illustrated, the current in the wire was composed of electrons that flowed from the negative pole of the battery, the cathode, to the positive pole of the battery, the anode. The anode or positive is at the top of the battery, and the cathode or negative is thought to be at the bottom of the battery. The flow of electrons is opposite to the direction of conventional current. The battery provides the electromotive force that pushes the electrons through the wires of the circuit. Electromotive force is measured in volts. In some ways, it's similar to the potential energy stored in an object at the top of a hill. The object might roll down the hill and lose potential energy. And in this analogy, the electrons flowing down the voltage drop or potential difference is the same as the way they traverse or move through the circuit. So when an object is at the top of a desk or a hill, such as a basketball, and you just leave it there, it has a lot of potential energy because it can easily get knocked over and move down the hill. Once it reaches the bottom, there's no place else to go, so it has lost that. So there is a potential difference from the energy at the top of the hill and the energy at the bottom of the hill. It is the same with a circuit. So potential difference is often referred to as electromotive force and vice versa. So you've heard the word voltage, potential difference, and electromotive force. They're basically meaning the same thing in our simple circuit. Voltage can come from many sources. We have wind power, water power, solar power. So all such devices create a potential difference and can supply current if connected to a circuit. A special type of potential difference is known as electromotive force. The EMF is not a force at all, though. It is a term, electromotive force, that came about due to historical reasons. It was coined by Alessandro Volta in the 1800s. It is why we use the unit of volts to measure the potential difference or the electromotive force. So we use voltage because it came throughout history from the name of the man who first coined the expression electromotive force. Here is a simple series circuit. We have a battery, a 12-volt battery, 6-volt battery, sorry. And it has a positive and a negative. So the anode and cathode. And if you look at this wire, it will go down and connect to the switch here. And this would have to be pushed down for it to be on. And then the current. So the current is flowing in this direction. The current is flowing out of the positive terminal through the switch, when the switch is closed, through each of these little lamps and lights them up. One thing to notice, as this, the voltage forces the current to come through here, the current will stay exactly the same no matter where you are in the circuit. The resistance, every time you add one more of these little lamps, your resistance is increasing. Each one of these causes some resistance. So the more you add, the more resistance. So the total resistance is the sum of all the resistance. At every one of these places, some of the energy that comes from this battery, some of it's going to be used up here, some of it here, some of it here. So the sum of the voltage from each of these smaller pieces in this circuit will add up to the total voltage. So in a series circuit, current flows only in one direction. It also has just one path to flow through. That's it. When we look at this diagram, there are two paths for the current to flow through. Here is the light bulb or the lamp, but when these little batteries, these symbols are representing the electrons. See how there's a lot of electrons in these? 3, 3, 3. So because they're 3 volts, each of these has their electrons, and the electrons are going to come out of this one. They meet up over here, and when they get to the lamp, the energy from those batteries is going to be used. So right now, these electrons have to get back to the batteries to get recharged. Once they're recharged, they continue. Once I get to this point, when the electrons are here, they can choose to go right or they can choose to go up and then right. So there are multiple paths. If there are multiple paths or more than one path, we have a parallel circuit. So this is a diagram of a parallel circuit. DC, or direct current. It's current that flows again only in one direction. Examples would be batteries, fuel cells, rectifiers, generators with commutators. And in this little diagram, we have a battery. And right now, these arrows are actually showing the flow of electrons. If I wanted to demonstrate the flow of current, all of the arrows would be facing the opposite direction. Let's look at a series circuit on a DC current. One of the key components is to remember that Ohm's law applies to the entire series circuit as well as each individual component. Ohm's law shows that relationship between current, voltage, and resistance. And we can also throw power in there. But when we first looked at Ohm's law, we looked just at E equals IR, and then we rearranged that formula. So what I have for you on this here slide is the entire Ohm's wheel, which has your amperes, I, your intensity of current, your ohms, resistance. Ohms is the unit of measurement for resistance, your electromotive force measured in volts, and your power, which we will use P instead of W, your power measured in watts. I had given you this circle before, and it's on the back of several of my t-shirts and one of my sweatshirts, E equals IR. If you know E equals IR, then you can just rearrange the formula to isolate the current or to isolate the resistance, or simply use the circle. And if you are looking for the electromotive force, put your finger or your thumb over the E, and you will have I times R side by side. If you're looking for the current, put your thumb over the I, and you will have E over R, or E divided by R. That's where this comes from, and they demonstrate that over here. If you're looking for resistance, we cover that. If you're looking for current, you cover that, and you have E over R. So it's a simple way to remember which way to go. There are certain properties of a series circuit. So in a series circuit, the current will never change. Current remains the same throughout the circuit. The total voltage will equal the sum of the voltage drops along the circuit. And the total resistance will equal the sum of the individual resistors. I like this little demonstration here. It's like a chart that shows you all the properties of a series circuit. So electromotive force, current, resistance, power. Electromotive force, if you have 3 resistors, add them all up, you have your total in volts. Your current, notice this line just says equal. It means no matter where you are, the current remains the same, and we say they are measured in amps. The resistors, if you take the sum of all of the resistors, all 3 of them, add them together, you will have the total resistance measured in ohms. And power, that's where the P is, you can add up the power used at every one of the resistors, and you will have the total wattage or the total power. And E subscript T, or E subscript total, is the voltage from the first plus the second plus the third. Same with resistance. Let's go to resistance. Total resistance is the resistance from the first plus the second plus the third. Notice current is different. Current, they all equal the same. Whatever the total current is, it is the same at the first resistor as it is at the second and third. So I1 equals I2 equals I3. And power, like the resistance, you would have to add up the individual power or wattage used at each resistor. So I hope you find this helpful. When you're ready to do the homework, or before you do the homework, I would like you to take a look at the other 2 videos first. The first video is called Electrical Circuits, and the second one is called DC Circuits Explained. They're both relatively short, and they contain important information. Sometimes hearing different people explaining the same concept from different perspectives can be helpful. The mathematical calculations will be the next lesson. So you do have some questions to complete, and those questions are on all 3 videos. So it's on the 3 videos, and there is a PowerPoint uploaded in Google Classroom for you, or Google Slideshow uploaded without me speaking over it. So I do hope you find this helpful. Have a great day. Bye.